Hi, and welcome to What Circuits. This is video number 4 in our Introduction to Filter Design series. So in the last video we looked at building and designing and building a switch resistor type filter and how that worked quite well, but as we talked about there are some limitations to that. And we also talked in the last video about how you can use analog multipliers to get around some of those limitations. So in this video we're going to build up a filter using analog multipliers. But we're also going to talk about some of the other techniques that are out there as well. Won't actually get to building them, but we're going to talk about them and cover them so you can look into them in more detail if you need to. So yeah, let's get on and build and design something. So we've taken the filter from before, and as you see we've just modified this lower part of the circuitry, so it's now got multipliers on instead of the switches that we had there before. The rest of the circuit is very straightforward, it's just some resistors and bits and pieces just to set up the multipliers so they've got the right gain, which in this case is times 1. We've taken the input signal here and modified that, so now instead of the control signal for the switches, that's now the control signal for the multipliers. So I've just got this connected up to a waveform generator. I'm feeding in a DC signal into there, so that means we can just control that DC signal and change the gain and therefore the cutoff frequency. Lots of decoupling caps, especially as we've got split rail supplies on this. And then, as before, we've got the power supply coming on here. So this is now full plus minus 15 volts. We're now not limited by the switcher rails, so that's just because which switch RSCs I had in stock. Again, we've got the analog discovery input hooked up to here, and then we've got the output, so currently connected up to the low pass output on there, and we just move that around the board. So we're all ready just to set this up and take some measurements. Right, so we've got the network analyzer function running again. Now, you notice this curve is quite curvy again. The reason being that I'm taking a lot of steps just to make this run a lot faster, just so we can cover a few steps in this video. So we're only covering what we're doing, about 2.5 decades, and it's going from 1 kilohertz up to 500 kilohertz. So I've got the control signal on coming into the filter set at around 10 volts at the moment. So this is on about the highest cutoff frequency. So if we put our cursor over here, we can see it's minus 3 dp point is just around here at about just over 50 odd kilohertz. So let's see what happens if we bring that control signal down. So I'm going to bring it down from 10 volts down to 5 volts. So you see an immediate drop down there, and now what we should see is the cutoff frequency coming down. And indeed we do. So let's just do another quick measurement of the cutoff frequency. So here we are, about 25 kilohertz. So we've halved the control voltage, and we've about halved the cutoff frequency. And let's bring our 5 volts down to 1. And if we just measure that cutoff frequency again, there we are, about just over 5 kilohertz. So from 10 volts to 1 volts, we've got 1 decade of change on the cutoff frequency. It's working very well. What it does illustrate, though, if you try and put too small a voltage in, you're going to end up with very high precision required to really get an accurate cutoff frequency. Now the multiplier we're using in this, which is the AD734, actually has a configurable denominator. So you can actually tell it to divide the control signal by a certain amount. So in this case what we can do, we've got the divider set as a ×1 divider at the moment, so that will give us 1 decade of change. If we then change the divider, so it then divides by 10, that will give us another decade of change, but we can still use the same 10 volt to 1 volt control signal, which means we can get really quite good accuracy. And the other thing to point out, it's just been mentioned, you can see that the graph, when you start to get over down to sort of low attenuation, starts to go quite wobbly. And the reason being, by the time you're down at sort of minus 45 dB, remember you're talking about a signal which is in sort of microvolts. So just any kind of strain noise or any kind of measurement error really starts to make a big difference with this, and this is why right at the beginning we talked about construction techniques, and they're really critical for building and measuring this type of filter. And just one gotcha to mention as we're talking about making variable filters. So we've talked we can adjust R4 and R5, adjust them over a span of sort of 10 to 1 or 100 1, and that's going to give you a range of 1 decade of filter frequency or 2 decades of filter frequency. If you want more than that, what you might want to do is to actually start switching in different capacitor values. So if you put some analog switches in here, you can just, turn on your 1 nanofarad capacitor, or turn on your 10 nan, or turn your 100 nan capacitor, and that's then going to really expand your range quite widely. So this means you can actually make your resistor selection much less critical. It means you can get away with some slightly cheaper or slightly easier control options. One thing to be aware of though, note in this formula here that R7 depends on C1. So therefore when you start changing this capacitor value, make sure you can then also switch in some different resistor values here at the same time. And generally you can actually do that. If you've got analog switches, you can have an analog switch here to switch in your capacitor, an analog switch here to switch in the appropriate value resistor, and you can just send the same control signal to both switches. So that means the two are always kept in sync, and it means your Q is kept constant if that's what you want. You can also have control over your Q. But yeah, just a quick little note for as you change ranges there, it can catch people out really easily. So we talked in the last video about 3 different ways of varying the frequency. So that was using a potentiometer, using switch resistors, and using multipliers. And then we looked at 2 of those in detail, looked at switch resistors and multiplier solutions in a lot of detail. So let's just cover 3 more solutions in this video, a bit briefer than before, but 3 it might be of interest. So obviously the multiplier worked really well in the last video. So one other option, as opposed to going for a full analog multiplier, is actually go for what's called a multiplier and digital to analog converter. So on this, in a similar way to the multiplier, you feed an input signal in, but then the other signal is a digital signal, either via an SPI bus or via a parallel bus externally available, and that just gives it a digital number to multiply against. So the nice thing is you can know that the digital number going into both sides is going to be exactly the same. There are some tolerance issues with MDACs. It's not that bad and it is workable around, and it's a really interesting solution. Again, it's one that is really quite a viable solution. They're also not that expensive and cheaper than analog multipliers. Another option which I looked at briefly, but you might want to investigate a bit more, are operational transient impedance amplifiers. These are a bit like an op-amp. They take effectively a differential voltage in, but then they give out a current which is proportional to the differential input voltage multiplied by some number. Multiplied by the sum number is where we can start to apply a gain across the 2. One downside of OTAs is just that they're not that available anymore. Not a lot of people make them. And indeed, if you look through the internet and find a lot of the circuits where they show applications of OTAs in variable filters, a lot of the parts of reference just can't be bought anymore. But when they're around, they weren't that expensive. Quite a nice little solution. And then one of the other ones I'm going to cover is actually switch capacitor, which is subtly different to switch resistor. So this is a technique that's actually used a lot inside integrated circuits to replace resistors, because when you're building an integrated circuit, putting a resistor in is really expensive. You have to get a very thin bead of conductive material, silicon, and then you have to snake it around, and that uses up quite a lot of area. Whereas building capacitors and switches, well, capacitors are still quite large, but switches, nice and straightforward. So if you take a switch capacitor, you've got an input and an output, and you've got a changeover switch here. So initially, the capacitor is connected up to the input, and a certain amount of charge goes in, and the capacitor fully charges, because we haven't got a resistor in the way. We're just going to charge it absolutely completely, and we're going to charge it all the way. So there's X amount of charge here. So then, as we move the switch across, so we now connect capacitor up to the output, all this charge moves to the output. And especially in a circuit like this, where you've got, you replace R4, say, with a switch capacitor, and you've got an integrating capacitor up here, as long as you make this capacitor quite a bit smaller than C1 and quite a bit smaller than C2, you can flick it, you can turn that switch across, and depending on the speed at which you change that switch, or the amount of charge you're putting through, and therefore the faster you do the switch, the more charge is getting through per unit of time, it's effectively like having a lower value resistor there. So it's quite an effective technique. The downside is you really want a nice precision capacitor there, so you know how much charge is being transferred, and you want nice low loss switches here. Now if you're going to look at this technique, I'd highly recommend looking at the linear technology part. LTC 1043. So it's a really simple integrated circuit, and all it is a switch capacitor block with all the inputs taken to the outside. So generally actually driving that is a little bit more complicated than driving something like a switch resistor. So a switch resistor takes a pulse width modulation signal in, which of course is really readily available on basically every single microcontroller out there. This, you want a variable frequency signal. It's a little bit more complicated to generate, but not rocket science. And again, you want your switching frequency here to be nice and fast, much faster than your filter cutoff frequency. And so that's implying using the low pass output. When you start putting the high pass output on, you're still going to get some kind of noise coming through the filter. So you might want to put a little notch filter in the output just to try and remove that, take that noise out, something, you know, some methods like that. So that's just a few more options, different ways you can do variable frequency filters. So we've looked at using analog multipliers to vary the cutoff frequency in the filter, and you see it works really well. So as I said, this has got some advantages, disadvantages over switch resistors, which was the other technique we looked into in detail. We cover some of the other techniques, some of the common techniques, and a few of the less common techniques. And so what we're going to do with next video, we're going to take this forward. We're actually going to get some printed circuit boards made and start taking some bit more detailed measurements and see can we actually get the variation over a large number of decades, so a really wide performance filter. And as we talked about, some of the limitations and issues with doing that, and we'll see those covered in some actual measurements next time. So as always, if you liked it, please give us a like or a thumbs up, and yeah, until next time, thanks.